Step 4, EMF, lesson 27, addition practice. Okay, question 1. So you have to prove that OX is perpendicular to AC. Okay, so let Y be the intersection of AX and OC. So this point over here. So now ACB is 90 degrees, ACB. ACB, yeah, this one right here. So you have learned in EMF that if there's a semicircle bounded inside, if there's a right angle bounded inside the semicircle, then this angle here at the circumference will be the right angle. So put ACB is 90 degrees, right angle in the semicircle is the reasoning. And now OX and BC are parallel to each other, right? So by rule of alternate angles, this is 90, and this should also be 90. So therefore, OX is perpendicular to AC because you proved that this is 90 degrees. Okay, so this question 1 done. Let's go to question 2. So question 2, right? You will have to associate one angle with another and then draw a comparison with another pair. Okay, so it goes like this. ABD is parallel to BD. I'm sorry, not parallel. ABD equals to BDC. So ABD, so this is the angle here, is equals to BDC. So this is by rule of alternate angles. Okay, so now that we established this, the next thing we're going to write is this will then equals to half of BOC. Because as you have learned in EMF, angle at center, BOC. Angle at center will always be twice the angle at the circumference. So this angle will be twice of this angle. So in other words, if I take this angle, BOC, and multiply it by half, I will get BDC. So as I mentioned earlier on, right? So we made a comparison with this two, correct? Which now also means that ABD equals to half of BOC. Okay, so keep that in mind. So half of BOC means it will equals to half of OCD. Why is this the case is, this is OCD, OCD, and this is BOC. Okay, so why is there a link between OCD and BOC is because BOC and OCD are equal. By rule of alternate angles, this equals to this. Therefore, half of this will equals to half of this. Okay, so from here, we can now draw a comparison where ABD equals to half of OCD. In other words, 2ABD equals to OCD. Okay, so next what you write down is angle BEC, angle BEC. This exterior angle on the outside will equals to this angle and this angle due to exterior angle of a triangle. All right. So from here, what we can do is we can replace it with ABD and 2ABD. Okay, OCD equals to 2ABD, right? So OCD equals to 2ABD and BDC equals to ABD. So this in total will equals to 3 of angle ABD, proved. So that's done with question 2. Let's move on to question 3. So now prove that triangle TRQ is similar to triangle TPS. Okay, so firstly, this angle is common. It is shared by both the small triangle and the big triangle. So QTR is a common angle. Okay, next one, we're going to use angle in opposite segment. Okay, but it goes like this. Now, QRT equals to SRQ. So basically this angle plus this angle is 180 degrees, right? So this will equals to another two angles that equals to 180 degrees. Okay, so recall what you learned in EMF, angles in opposite segments equals to 180. So SPT, this angle here, plus SRQ, this angle here. This two will equals to 180 degrees. So from here, you'll see a common angle, SRQ. You cancel this two, you will arrive at this conclusion, where QRT equals to SPT. QRT equals to SPT. Okay? So therefore, TRQ is similar to TPS. Done. Okay, so in part B, right, you can just draw the conclusion based on the two triangles being similar. So just key in your values, you will get TP equals to 60. Okay, so now I'm going to prove that ECF and FCG are similar. So firstly, the angle ECF is common. Second, using the alternate segment theorem, the angle outside here, ECP, will equals to GFC. So it's kind of like a weird sort of alternate angle theory, where if you draw a line, this tangent, connect it up to one point here, you bring it down this way, this angle goes to this angle, okay? So that would mean ECB equals to FEC using alternate angles, which means this angle equals to this angle. So that will prove that this will equals to this. So we can draw a conclusion that GFC will equals to FEC. These two angles are equal. So therefore, EFC is similar to FCG. In part B. Sorry, not part B. A part 2, hence show that EC times CG equals to CF squared. So from here, draw the conclusion based on two triangles being similar. Do your cross multiplication. Now CF and FC, they are just the same thing, just written in respective order. So CF times FC is basically CF squared. So that's how you draw that conclusion. Sure. Okay, part B. By using similar triangles, show that the following equation works. Okay, so you have to show that FEG is similar to CEH. Okay, so FEG equals to CEH, vertically opposite angles. FEG and CEH, vertically opposite angles. Then FGE and CHE. They are the same angles because angles in the same segment. If you realize, right, this angle and this angle are created using the same base, CF. That's why it's called angles in the same segment. Okay? Meaning you branch out two triangles based on CF, right? And if you connect it to the circumference, this angle and this angle will be equal. So if you prove two angles, if you prove two angles are equal, you don't have to prove the third one. So you can immediately draw the conclusion that these two triangles are similar. So based on the conclusion, you can create this, cross multiply. So you will have FE times CH on the left equals to EG times EC. So EG is based on CG minus CE times EC. So when you multiply this in, you get CG times EC equals to CE times CE. So this is CE squared. CG times EC will be equals to CF squared. Show. Okay, question 5. Show that the triangle ABC is similar to triangle ADQ. Okay, so for part A, using alternate segment theorem, CPB equals to CAB. So CAB equals to ACB using alternate angles. So take note, this one is alternate segment theorem. Then CAB equals to ACB. This equals to this using alternate angles. Just the two lines are parallel. So again, revert back. So ACB will equals to QAD using alternate segment theorem once again. Which means this ACD, ACD, yeah. So using alternate segment theorem, so therefore CAB equals to QAD. So that's one. Next one is TBA equals to BCA using alternate segment theorem. Therefore TBA equals to TAB. Tangents to the circle. So since TAB equals to BCA, therefore BCA equals to DQA. So both triangles ABC and ADQ are similar. Okay, part B, show that 2 times the angle of CQA equals to the following on the right. So for part B is what we can write first. 180 minus the angle BTA divided by 2 equals to TBA, the sum of the angles in the triangle. Okay, so before we go on, using alternate segment theorem, TBA equals to BCA, right? And BCA equals to DQA. So you can draw the conclusion that TBA equals to CQA. So this is what we can write now. 180 minus BTA divided by 2, the same equation, replace TBA with CQA. Therefore, 2 times CQA equals to 180 minus angle BTA. So you're just manipulating the formula over here, all right? So that's all for today. See you on the next one.